Hello, this is Vishnu. My assignment topic is 3-bit ADC SAR. It basically contains 4 building blocks. First one is DAC, digital to analog converter, and another one is the operational amplifier based comparator. Another one is counter, and another one is SAR, which is simple some successive approximation circuit. So I have designed a SAR circuit. The algorithm which I used for designing this I will explain you here. Instead of using a ring counter, I have used a down counter here, which counts from 7 to 0, but I have stopped the counting value whenever it reaches 1. So here 111 in the sense its value is 7, 6, 5, 4, 3, 2, 1, and whenever it reaches 1 from the next clock cycle also it should return 1 only. 1. So now the input which I have considered is 3.5. The analog equivalent of 111 which we get after feeding this value into DAC is greater than 3.5. So the comparator output will be 0. That is since we have given here also 3.5, the analog equivalent which we got here is greater than 3.5. So the comparator output should be minus VSAT, which will be converted to 0 using a NOT gate. Using a NOT gate here. So in the next state of the counter, then also the value is greater than 3.5. Output from the DAC is greater than 3.5. So the comparator output is again 0. And in the next clock cycle we got the comparator output as 1. So the main thing to note here is whenever we get 1 in a particular clock cycle, from the next clock cycle it doesn't matter, we always get 1 here in the output. So this is the main advantage using a down counter. It is basically counting, taking a bigger value and gradually decreasing, comparing with the input. This is basically these 3 flip-flops, and this circuit is basically a counter, which is down counter. These 3 will be like down counter, and these are used to limit it to 1 after reaching 1. So whenever the counter reaches 001, it should always stay at 001 as I previously said. So that can be done using these. Okay, and the resistor and capacitor RC circuit is used because since the previous states of the flip-flops are not known, there may be the 001 may also occur at the starting stage itself. So the counter will stop counting when the first cycle is 001. So in order to avoid that, I have used this RC circuit. Since the initial state time is very less, the capacitor can't charge up to 2.5, which is the threshold value. So the output would be 0 itself. So in this way we can avoid the ripples that are occurred in the before first state, that is previous state of these flops. So that's why I use the capacitor here. In 1 microfarad I got means I have calculated these using the charging and discharging times of the capacitor. And this is the DAC circuit. It takes 3 inputs from these outputs of the counter and generates an analog value here. This analog value is compared with the reference value, which I have used as, I have taken this as 3.5. The reference value which I have taken here is 3.5. So it compares the 3.5 with the counter output and returns either 0 or 1. As I previously said, if the comparator output reaches 1, the counting of this counter should be, even though the counter counts the cycle, these values should be stored. So storing of these values is done in these 3 flip-flops. So whenever the output reaches 1 here, those cycle values should be stored in these 3 flip-flops. So I have feeded this output to a flip-flop so that I will be storing these values in the next clock cycle. I have taken, if you can see here, I have given these values as inputs to these flip-flops. That means if I get 111 here, in the next clock cycle I will get 111 stored here. But the output which I get here is in present, and here are the previous values. So I used switches here. Without using this, if I get if my required value to be stored is 111, let it be. So whenever I get 111 here, the output would be 1, and when I directly connect these to these, the values which are previously stored in this will be returned as outputs. But I don't want that, so I have used a flip-flop. This is used because in the next clock cycle it will return the value as 1. So in the next clock cycle, in the sense, our required values will be stored in these 3 flip-flops at that time. So for doing that, I have used 3 switches, which are like depending on the output of the comparator. If it is 0, if the comparator output is 0, the input of these flip-flops should be taken from outputs of these flip-flops. That means outputs of these flip-flops are connected as inputs of these flip-flops if the output is 0 from the comparator. If the output from the comparator is 1, the values are to be stored in these flip-flops. So in order to store the values, the flip-flop should always return the same value. That means this can be done by feeding the output as a input to the D flip-flop. So I have used a switch. When the output is 1, the switch connects the input to these flip-flops to the outputs of these flip-flops so that the value gets stored in these flip-flops. Finally, I have taken the output from these 3 flip-flops and I have measured using an oscilloscope. Let's measure it. Now let us run the simulation and see the results. This is the LSB, and this is the middle one, and this is the MSB. So we shall give 3.5 and see the results. So if we are giving 3.5, the output should be 101 from the ADC circuit. Let us verify whether we are getting that or not. As I said previously, we will get output after 2 clock cycles. Yeah, 2 clock cycles are done and the output is fixed as 101. This is the required output. So it's working for 3.5 and let's see for 2 volts. So if we are giving 2, we should get 011. Let's see if we are getting that or not. I can rerun this. So that's it. Here we are getting 0 1 1. So we got the result for 2 volts as well. So let's check for 1 volt. For 1 volt, the ADC output value should be 0 0 and 1. So let's check. Yeah, we got that 0 0 and 1. So the circuit which I used is correct and I got the similar results. Thank you.